Welcome to the start of Unit 2, Metabolism and Energy. So the overview for this lesson, we're going to begin to understand the chemical changes and energy changes that occur during cellular respiration. So this lesson is just a general overview, and then we'll look at glycolysis and the Krebs cycle and the electron transport chain, which are three of the steps in a great deal more detail. So by the end of today, you should be able to give me the general equation for cellular respiration, define and give examples of the terms that are listed, and state the laws of thermodynamics and use them to explain the free energy change associated with metabolism. So I'll start with some definitions, and then we'll look at energy and thermodynamics. And from there, we'll move on to free energy and a quick little intro to what you're looking at later in the week. So some key terms that you need, make sure you're jotting these down on your, either the PowerPoint, you're following through, making sure you're listing any questions, or if you've downloaded the Cornell notes, you're jotting these down on your Cornell notes. So metabolism is the sum of all of the chemical reactions that occur in the cell. So basically every chemical reaction that occurs in the cell is metabolism. A metabolic pathway is a series of steps that occurs in sort of part of metabolism, and I'll show you what a metabolic pathway would look like in the cell in a second. But it's a series of enzyme catalyzed steps. Catabolism or catabolic reactions are reactions that break down compounds into smaller molecules, so taking those macromolecules and breaking them down into their monomers for energy. And anabolic reactions use energy to build large molecules from smaller ones. So we'll talk in our genetics unit about protein synthesis, DNA replication. All those processes are anabolic, building the macromolecules. So here we need both pathways in order for our cells to function. We take larger food molecules and we use catabolic pathways to break them down. These can also be structural molecules. So keep in mind, we're not just talking about carbs. We're talking about amino acids and things like that. So we'll take our food molecules, we'll break them down through catabolic pathways into the small molecules that make them up, the monomers. So you can see here, this big long chain of circles has been broken down into little circles. In the process of this, we lose heat, but we can also create useful forms of energy. And when we put the small molecules back together to make something that's useful for our cell, that requires an input of these useful forms of energy. This is when I said I was going to come back to metabolic pathways. This is a very small slice of the metabolic pathways that happen in the cell. So for example, if you look here, this is glucose 1-phosphate, which you'll worry about a little bit more in a second. Glucose 1-phosphate gets converted into glucose 6-phosphate, fructose 6-phosphate, yada, 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 through this sort of circular pathway. And this sort of straight lined circle is the slice of metabolism that we're going to focus on in this course. But if you look, we have other ways we can make fructose, or we can use fructose, depending on what we're talking about. We can make ribulose 5-phosphate, and then from that ribulose 5-phosphate, we can make the amino acid histidine. We can make AMP and GMP, which are nucleotides, and we'll learn more about those in another unit. Tryptophan, tyrosine, so these are our amino acids. So these would be biosynthetic pathways. So all of these are different metabolic pathways in the cell, but sort of the root pathway is this one that we're going to look at this year. So here, this is glycolysis, and this is the Krebs cycle. And those two terms are probably new for you, but they won't be for long. So we need to understand what energy is. Energy is the ability to do work, so to change or move matter against an opposing force. So to pick a book up against gravity, that's work. The opposing force is gravity. There's different types of energy. There's kinetic energy, which is the energy of motion, and potential energy, which is stored. So if I held a book up about 3 feet above the ground, that book has potential energy. It's not moving, but it has gravitational potential energy stored by virtue of its position above the earth. When I drop the book, it has kinetic energy. It can do work by making other matter move. So if I created some sort of Rube Goldbergian contraction or contraption, I could hook a water wheel up underneath that book that I was holding up, and I could continually drop books on the water wheel, turning the water wheel, and use that to do work somewhere else. So moving objects do work by making other matter move. Thermal energy might not intuitively seem like a form of kinetic energy, but it is, because thermal energy or heat energy is the energy that comes from particles moving in random directions. And the other two examples, electric potential and chemical potential. So when we talked in Unit 1 about those potential energy diagrams, which you're going to see in a second, when a bond is formed between two atoms, energy is released, but it takes energy to break the bond. So remember, our potential energy diagram had a steep upslope where energy was being input to break the bond, and then we had a downslope where the energy was being released, and that point up at the top was the activation energy. The amount of energy to get up to the activation energy is also known as the bond energy. It's basically the energy that's stored in those chemical bonds. Energy in chemical reactions, it's usually released as heat. In living cells, we do release some of our energy as heat, and that's actually why when you get cold, you shiver. So if you get cold, you shiver because you're making tiny contractions in your muscle cells, and those muscle cells then require energy to do the tiny contractions, and a byproduct of that energy is heat. So you shiver as a source of thermal energy. But thermal energy is actually wasted energy in our cells. We capture the energy in a compound. We need to understand the laws of thermodynamics, so the laws that govern energy and energy flow, in order to understand the changes in energy in our cells. So when we talk about thermodynamics, and those of you who've taken grade 12 chem already, I know you're probably crying when you see system and surroundings and thermo, but don't worry, we're not going into anywhere near the depth that you looked at last year. When we talk about thermo, we talk about a system, and we talk about surroundings. So the system is the particular thing that we're studying, and the surroundings is everything else in the universe outside that system. So the first law of thermodynamics is that energy can't be created or destroyed, but it can be transformed from one type to another, or transferred from one object to another. So we also call that the law of conservation of energy. And all that means is that when a chemical reaction occurs and energy is released, the energy has to go somewhere. It can't be destroyed. So the energy either is transformed into mechanical energy, it's transformed into thermal energy, or it's trapped in new chemical bonds, but it can't simply disappear. The second law of thermodynamics is that during any process, the universe tends toward disorder. Disorder is also called entropy. So the second law of thermodynamics is that everything in the universe tends to move toward a state that will increase in entropy. And usually that means that energy is going to be wasted out as heat. So you can see, this is, I think, a good example. If I randomly threw bricks, the highly improbable way, like it takes energy to get bricks to form a wall. If I just threw them randomly, this is much more probable, right? So the natural state of things is to proceed toward disorder. Free energy is energy available from a chemical reaction that is actually available to do work. And we give it the symbol G, and that's short for Gibbs free energy. The energy contained in the molecular bonds is enthalpy. So mathematically, and I'm never going to make you do this unless you're in AP. If you're in AP, you are going to have to do this calculation. mathematically what that means is that at a constant temperature, pressure, and volume, the change in free energy for a chemical reaction is equal to the energy stored in the bonds minus the energy lost as heat. So we call this the entropy term or the disorder term. Basically, it's the energy stored in the bonds minus the amount of energy that has to be kind of wasted. And the difference there is the amount that's actually going to be available to do work. And we can talk about, we've talked about exothermic and endothermic reactions. Endergonic and exergonic are basically the same thing as endothermic and exothermic. So an endergonic reaction is one that requires an input of energy in order to occur. The delta G is positive, and the products of that reaction contain more energy than the reactants. So the enthalpy is high, the bond energy is high, and the disorder is quite low. Exergonic reactions release energy, and the delta G is negative. The products of the reaction contain less energy than the reactants, where the enthalpy is lower and the disorder is higher. So the difference is that you can sometimes have endothermic reactions that are exergonic. An exergonic reaction occurs spontaneously, which means that you can just mix things and it will happen, even if it does release or require heat, let's say. So think of an ammonia cold pack. If you've used those single-use cold packs, you break a blister pack in them, it causes water to leak out. The water begins to dissolve ammonium chloride or ammonium nitrate or some similar compound. And that's an endothermic reaction. However, it's an exergonic reaction because the disorder term is actually much higher. So even though the enthalpy might be low, the amount of disorder of the reactants is higher. So it will occur spontaneously without you having to add heat. So this is what I was talking about before. Spontaneous reactions are those where the difference in disorder is greater than the enthalpy of the bonds, so where delta G is negative. This gives you a visual of endergonic and exergonic reactions. So again, very, very similar to endo and exothermic. So what? Why do we care? Why am I teaching you thermodynamics when you're in a biology class? I asked that question every day when I was forced to take thermodynamics. I can't speak to university thermodynamics, but to this level of thermodynamics, you do need to understand whether a reaction is going to occur spontaneously in connection with its activation energy to predict how it's going to happen in a biological system or what needs to occur. And typically what we do is we use these catabolic reactions, these energy yielding reactions like glycolysis, Krebs cycle, cellular respiration, in order to power the anabolic reactions in our cells. So we capture the energy that's released from these catabolic reactions in small molecules in the cell, and that small molecule is ATP, which we kind of briefly talked about with the sodium-potassium pump. And then we take that energy and use it as an input to drive the anabolic reactions, because we still need those anabolic reactions. The whole reason these catabolic things happen is because we need the anabolic things to go forward. Electron carriers are going to become very important in this. So we talked about in our biochemical reactions, redox reactions or reduction and oxidation reactions where electrons are transferred. The cellular respiration process that we're looking at utilizes a lot of these electron carriers. So we carry energy in the form of electrons, in some cases. So electrons passing from one molecule to another carry that energy with them. A reduced molecule has more energy than an oxidized molecule. So that was a question in your homework last unit, and I said we'd talk about it later. So things that are highly reduced, like glucose, have a lot of energy stored in them. Things that are highly oxidized, like carbon dioxide, do not. And we're going to ignore FADH2 and NADH2, the last two molecules on that slide. They are kind of the prime energy electron carriers in our cell. So cells use four main biological pathways to capture energy. I've mentioned at least two of them, I know, several times during this screencast. Glycolysis is the initial breakdown of sugar. Pyruvate oxidation is kind of an intermediate or prep step. The Krebs cycle is the continuation of the sugar breakdown, and electron transport is actually sort of the payoff phase where we really see all of the energy that was stored in that sugar molecule get converted into usable energy by the cell. The overall equation for cellular catabolism is C6H12O6 plus O2 breaks down into CO2 and H2O. Obviously, that's not balanced. It's also the same equation for the combustion of glucose. However, if we look at the combustion of glucose, the activation energy is too high and the amount of energy released is too great. So either way, we'd cook cells. So we need to carry out this process in several steps with lower activation energies and lower electron yields. So this is a potential energy diagram that we already looked at in Unit 1. Here is the energy of glucose and oxygen. So this is the bond energy of glucose and oxygen. This would be the bond energy of carbon dioxide and H2O. So you can see that there's a lot more energy stored in glucose compared to carbon dioxide and water. We have an input of activation energy, and then we have a great amount of free energy output via heat and light in the combustion reaction. In our cells, let's say each of these represents one of those four kind of processes. So really, this is actually a series of smaller reactions, not one. We've got glycolysis, pyruvate oxidation, the Krebs cycle, and electron transport. So now we have this reaction occurring in a series of steps, and each has a much smaller activation energy, so easily accomplished by enzymes, and it has a much smaller free energy yield. And that free energy is now not being released as heat. There will be some heat wasted, but it's being captured by molecules like ATP. And so this is kind of the overall framing of the process that we're going to spend the next few weeks looking at.